law of sines. This probably brings back some terrifying memories for you. High school trigonometry, remember that? Well, put aside all your fears, all your bad memories. Let's forget about that. Start fresh. Law of sines. Why sines? Why is there an S here? Well, there's 3 signs to think about. Let's label this triangle according to classical labeling scheme. Vertex A here and side A there. Vertex B here, side B. Vertex C here. And angles alpha, beta, gamma, like that. And the law of sines says something like A over sine alpha. So side A divided by sine alpha is A over sine beta, and that's, B over sine beta, and that's C over sine gamma. Now, the thing that nobody ever asks in high school is this. Yes, they're all equal. This equal to this ratio equal to this, and this equal to this. But actually, they are equal to what? And this is actually very interesting. And we're going to prove the extended sine law that what they're equal to is the diameter of the circle which circumscribes the 3 points. As we know, you can always draw a circle through 3 points. Okay, this is called a circumscribed, or I can call it an X circle, or circumscribed circle. I can always do this to a triangle. Okay, so I draw a triangle and then I can circumscribe a circle, and this thing has a center and this diameter, 2r, 2 times the radius. Well, that's what they're equal to. Now, if you know that, then extended law of sines. This is a lot more powerful than the usual sine law, because you can now prove things about triangles and circles that circumscribe them, and all kinds of other problems that they give you in competitions. All right, we need some tools, and I know what you're going to say. I'm going to draw a triangle right here, and you're going to tell me that, you can't do that. You have to first draw the triangle and then circumscribe the circle around it. Yeah, I know what you're thinking. But okay, you're right. The thing is, though, look, I only have one hand. I can't use a compass. I could do it with a compass. I want you to do it with a compass, but I can't do it because I only have one hand. All right. So we're going to first draw our circles and then put triangles inside rather than the other way. Now, we need some preparation, some theorems. And here's one theorem. If I have a chord like this, and I have this point, let's say, call it A. This angle is alpha. If I move this around, and everyone knows this theorem, this is a well-known theorem. This also alpha, A prime, you see? Also alpha. So the angle is invariant. Angle is invariant. I can keep going around like this angle is invariant. Beautiful, no? Okay, and same thing here. Below here I have another point. Let's call this B, this beta, this B prime. Beta, same thing. Another B prime, prime. It's also beta. So angle is all the same here. Good question is, are alpha and beta related? And the answer is yes. Let's see how they are related. Many people already know this theorem. I mean, it's a very well-known theorem. If I have a quadrilateral like so, the opposite angles like this are supplementary. Alpha plus beta is 180 degrees. Now, I think that this is not the best way to think about such things. It's better to think in terms of angles and chords. So, what we're going to do is like this. Look, we know that this is angle alpha, okay? And if I draw a point here, this is angle beta, and look carefully, we know this is quadrilateral. But let's forget about that. Let's just remember that alpha plus beta is 180. Now, I see that all of these alphas, they're all equal. And if I draw on the other side of the circle, all the beta angles, well, they're also all equal. But the important and amazing thing is that they're related to each other in an amazing way. Alpha plus beta is 180. So if I take this point and throw it across the chord to the other side of the circle, my angle becomes 180 minus alpha. So see, 180 minus alpha. That's really amazing. So as long as I'm on this side of the circle, alpha is the same. As soon as I launch the point to the other side of the circle, now this is 180 minus alpha. This is the same theorem as this, but I think that this is the right way to think about it, because this really helps us with this extended sine law and many, many other such things. A couple more points, things that we need. If our chord line goes right through the center now, let's say it's a center line. So this is a center line right through the center. Now, this is very special. This is going to be 90 degrees everywhere, no matter where I put it. One of the most beautiful theorems in geometry, you know. Think about it. And here too, look, beta is 90, alpha is 90. No matter where I put it, it's always going to be 90. And then alpha plus beta is 90 plus 90 is 180. You see? Exactly what we see here. Very special case, because now this is a center line. And if this is a center line, then this is diameter, and this from here to here, this is radius, and from here to here is radius. Okay. One more item of interest, sine. Sine theta. What is sine theta? Well, this is r, this is y. Sine theta is y over r. What about 180 minus theta? What is the sine of 180 minus theta? Well, this is still positive y, and that's r. You see? So we have discovered that sine 180 minus theta equals sine theta. Okay, this is something we need to know. All right, now let's go over here, start working on extended sine law. Let's take a triangle, 3 points. Not very good. Okay, let's try that again. A, B, C, alpha. Okay, I'll keep that as alpha. Now, here's the center line. I want to calculate the sine of alpha, but it's not that easy to do. So why don't I bring A to the opposite side of C, like so. Okay, I'm going to bring A to this position, this point here. Now what's happening? Well, as you know, this angle has got to be 90 degrees because of what we were just talking about over here. See? Okay, that's got to be 90 degrees. And also, as we know, okay, when you move, this angle is alpha. Now if I move it over to here, this angle is also alpha. Why? Because of this, okay? As I move my point, the chord does not move, the angle remains the same. Okay, let's go back here. So this is alpha and this is alpha. And so what do I get here? Well, sine of alpha. What's sine of alpha? Sine of alpha is opposite over hypotenuse. What is hypotenuse? RR. Opposite side is little a. Opposite side is little a. Hypotenuse is 2r. Beautiful. Okay, now. One more. Well, actually more than that, but let's keep going. Let's do A, B, C. Now I want to move B. I want to calculate the angle, sine of this angle B. Well, I can put it in opposition to A. Let's put it in opposition to A here. So I'm going to move B over here. Okay? So B is now going to be here. This line is going to be like this. This angle is going to be 90 degrees by the theorems that we just saw. And so, this is B, beta angle. This is beta angle also. They're equal because they're the same chord here. I'm moving this angle around, but the chord remains the same, so this angle has to be the same. And so what's sine of beta? Sine of beta is opposite side, which is B, divided by 2r, the hypotenuse. 2r. Beautiful. Over 2r. Now, I can do it again with C. Let's do C now. Okay. Let's do C. A, B, C, and this angle gamma. I want to move C so it's perpendicular to something. All right, let's put it over here. Put C here. And now, if I do that, this angle, 90 degrees, this is going to be gamma, same thing as this. Okay, I move it over here. Gamma stays the same because this chord is not moving. This length is C. And so therefore, sine gamma is what? C over R. R, hypotenuse is 2r, C over RR. So we have these formulas. Sine alpha is A over 2r. Sine beta is B over 2r. Sine gamma is C over 2r. So therefore, from this, we can see it's all equal to 2r. We have A over sine alpha is B over, well, it's 2r. B over sine alpha is 2r. C over sine alpha, sorry, C over sine beta, C over sine gamma is also 2r. See? Okay, they're all equal to each other, and therefore we have the usual law of sines. A over sine alpha is B over sine beta. And this is gamma, C over sine gamma, and that's 2r. Okay, this is the usual sine law, and this is the extended sine law. There you go. How do you remember this? Well, a little bit of dimensional thinking will help. A little bit of dimensional thinking will help. This is dimensionless, dimensionless, dimensionless. And this has dimension length, and this has dimension length. So the length has to be on top, and this is 2r, not 1 over 2r. Easy to make that mistake, but a little bit of dimensional thinking can help. Now, I have this blank circle left. Why is that? Because there's a case that's very interesting. This can happen. What if our triangle is completely in the upper half of the circle? Okay. You say, maybe no problem. Maybe no problem. Sure, maybe no problem. Okay, I can bring B into opposition. I can bring B down here. Now it's going to be in opposition to A, and I can do the same calculation like here. I can find sine. I can bring C down to here or here to be in opposition with B, and therefore I can find sine gamma, no problem. But what about A? I cannot bring A in opposition to B, and I cannot bring it in opposition to C so simply. But I can reflect it down here. I can make it jump over the chord line. Now I'm in opposition with B. Okay? Now I can do it there. This is angle alpha. What's this angle? Well, as you know, this is 180 minus alpha, right? Because we looked at this here. Okay? The angles here are all alpha, the angles here are all beta, and the relationship between them is alpha plus beta is 180. And also, let us not forget this. We did this for a reason. Sine of 180 minus theta is equal to sine of theta. And so therefore, this actually, sine of this angle is the same as sine of alpha. And now we can do it. It's easy to find this because this is going to be 90 degrees. And what's the sine now of 180 minus alpha? What's this? Well, it's opposite, which is A, divided by 2R. And again, this equals sine alpha because sine of 180 minus alpha is sine alpha. So I get, again, the same thing. I do not get something different in this special case. The special case is very beautiful, and I recommend that you study this special case very carefully. It really took me some time to imagine how it works, but it's really beautiful. You cannot just simply make a 90 degrees somehow. You have to jump it over the chord line and then make a 90 degree with one of these other ones, like so. But jumping over the chord line changes alpha to 180 minus alpha. But we are lucky because the sine of 180 minus alpha and sine of alpha are the same. There we go. The extended law of sines. The proof of it is really beautiful, I think, and teaches you a lot about geometry. And I recommend you look at these diagrams, you draw them yourself, you convince yourself of what's going on, you derive each one, alpha, beta, gamma, do it yourself. Keep this in mind. Alpha, 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 beta, beta, beta. Alpha plus beta is 180. If you like the extended law of sines, if you like it more than the usual law of sines, then click like on this video and subscribe for more stuff coming soon.